theory and simulation for a number of years. And just to show you that I really mean it, I do have an opinion I want to express, taking advantage of it. So I will now talk about what I would like to tell you in a reverse order. I'll give you my take-home message right now, and then spend the rest of the hour, whatever time we have, trying to defend myself. This is just to sort of get you to, in case you have to leave, in case I get too long-winded, I lose you somewhere, so at least what I'm going to say. And actually what I'm trying to say is not so subtle. It's very obvious, particularly given the audience here. I think it's actually an ideal audience to try this out. And also on the occasion of this first year progress review of Marvel, this is a good time to pop the following question. And the question is, how can simulation impact theory and modeling? Of course, this is a very general question, and I would like to answer that question in a personal way by giving you my answer with I would say 2-point-x illustrations. I give you two illustrations, and then the x is a fractional illustration, and that's fractional because it's still ongoing work and it's more for the future. So to introduce to you that indeed one can illustrate how simulation can impact theory and modeling, I would like to talk about mesoscale. So I have one slide to introduce mesoscale, and that also is nothing new, but nonetheless it could be used as a wrapper or context for the discussion of these illustrations. That's the first slide. So let me define the mesoscale science frontier as simply this little fuzzy zone here. This stands for mesoscale science. I call it a frontier because it is a place where that a lot of work can still be done. It's relatively new in a certain sense. It is new because it's a frontier that connects. On the one hand, you have science. On the other hand, you have applications. You have technology. Everybody knows that the ideal situation is to have a science and technology interplay. You drive the technology by doing great science, or vice versa. You pull in the great science by offering great technology, however you want to go with the arrow. And then the mesoscale also can be mapped onto this kind of dimensional axis, like in terms of capacity of doing the theory and the simulation. So you could do theory and simulation at the microscale or at the macroscale. Of course, if you want to impact technology, you should at some point reach the macroscale, because most of the technology is actually implemented there. Although that's not quite true, you can do great cancer therapy, drug design as well on the microscale. But nonetheless, the macroscale tends to be the sort of the application challenge. On this axis, you can talk about complexity. So you can start out with unit process, single defect, how does that move, how does that interact, all the way up the complexity axis to a situation where you talk about system level. By system level, I mean, how does a nuclear reactor behave in the presence of radiation, and that sort of thing. So there are all these sort of scales mixed up, and depending on where you want to go, you always have a point from A to B. Now, by mesoscale, I mean it is essentially the connection where you link the understanding and the design, let's say molecular scale design, to functional behavior. So by functional behavior, I have in mind here certain materials properties and behavior at the macro scale. That's what I will call functional behavior. And my two examples for the illustration, which I'll show you in the next slide, is one example is by functional behavior. It's like in a day like today, you can think about melting. How does a crystal melt? That would be a functional behavior. The other functional behavior that I'm going to discuss is the glass transition. That also, has certain simple context. So that is a rough definition of mesoscale. But throughout this whole talk, I will, if you ask me, if you're curious, you can say, where is the mesoscale in this slide? Where is the mesoscale there? There's mesoscale ideas and concepts sprinkled throughout the discussion. There are also buzzwords like, self-organized criticality, dynamical heterogeneity, and these are buzzwords, properly so, because they are the words that we're using to describe our current issues. And now you're going to have to say, is there a mesoscale in that? So there are different ways in which one can approach this frontier of mesoscale, depending on where you start. And even though I won't be able to cover very much of that, I just want you to know the potential is there. So let's go to the next slide. And this is basically the question I gave to myself in the beginning. If I were to come and talk to you about what I'm interested in, I think I'll just say, like I said before, how can simulation impact materials theory and modeling? And so I will do three illustrations. I call it 2.x because the third illustration, the plasticity one, is very much a current issue. But the first two, I think, are sufficiently settled that you can say that we can now at least give some reflections and talk about, what have we learned from these two illustrations. So the crystal melting, the mechanism of melting, which is not all that surprising, by the way, is something that I would say, depending where you start, you let me start, I will start about maybe 75 years ago, when Born first came up with a theory of melting and said, I can tell you what melting is, so on. And then so he did this back in 1939, 1940. So that's the first one. And you can see there's a little bit of progression here. Since I told you that amorphous plasticity is a current issue, so the furthest back we go is 75 some years. And so that's the crystal melting story. That's illustration 1. And the second illustration, which is actually the bulk of my interest in talking to you, is some relatively recent understanding of the nature of the glass transition. I would call that a sort of a 10-year history on that. Although the question that was raised with regard to the glass transition was raised some 40 years ago. So there's a long history. So in both of these phenomenon, there are long-standing interest and studies, and it's only fairly recently, with some hindsight, that you can begin to give some indication of what simulation has helped us in understanding these two phenomena. Well, with that as a background, then nowadays I can tell you I'm interested in bulk metallic glasses because the plasticity in these materials are very fascinating and technologically important. Then that gets me to the third topic, which I think I will have time to just touch on. But since there is going to be a SACAMP workshop here later this week, and I see the SACAMP director here, so it's my great honor that he's here. I want to mention that there's a SACAMP workshop, and there's of course a very close, intimate relation between Marvel and SACAMP. There should be, and I'm sure there is. And so I would save some of that for the people who also go to the SACAMP workshop. I won't say very much on that, but nonetheless, this is what I plan to do. And let me see now. So having said that, let me now jump right into this first illustration. It has to do with how does a crystal melt. That asking how something happens is not like when does a crystal melt. When does a crystal melt? Crystal melts at the melting temperature. So I can predict the melting temperature and get it right or wrong without ever facing the kinetics, that is the mechanism part. So it's both the when and the how. And sometimes the how is the tougher of the two. Because, okay, so and therein already lies a bit of a message in terms of the kinetics in these problems that we're looking at really matter. So let's go back to Max Born. 1939, he published a nice little paper in Journal of Chemical Physics with a great title. The title is Thermodynamics of Crystals and Melting. And if you look at that paper simply says it's well known that a crystal cannot sustain shear. Can't sustain shear. Liquid cannot sustain shear. So when the crystal loses the ability to sustain shear, its shear modulus C44, the elastic constant, at T equal to the melting temperature should be 0. That's a definition, an operational definition of the melting temperature. And Born did this because he had been actually working on crystal lattice stability, which he published the next year in this Proceedings of Cambridge Philosophical Society on the stability of crystal lattice 1, and there are 2 or 3 follow-up papers in which he, for the case of cubic crystal, he simply laid down these elastic stability criteria, C11 plus 2C12, which is basically the bulk modulus, has to be greater than 0, otherwise the crystal is not stable. C11 minus C12, which is a sort of a tetragonal shear modulus, has to be greater than 0. And finally, the C44, the rhombohedral shear, has to be greater than 0. So when these 3 conditions are satisfied, that's when the crystal lattice is stable. So you can see how he arrives at the melting criterion simply by thinking about this last criterion. Incidentally, this is the elastic constants they're really 4th rank tensors. It's a second derivative of the free energy with respect to certain strain tensors, which are 2nd rank tensors. And we know how to calculate these things with simulation. So that means now we can ask ourselves, is Born really correct? And at the time, Born got a lot of pushback. People did not agree with that being a theory of melting. For one, they say, where is the latent heat? Where is the volume expansion when a crystal melts? Usually there's a volume change. It's not necessarily always expanding. If you have silicon or water, when it melts, it actually contracts. So nonetheless, these are first order phase transitions. So where the latent heat and the latent volume change? Born had no answer for that. That's because Born's theory is, I guess you can call it thermoelastic in nature. It's a mechanical definition. There's another definition which is thermodynamic, which has to do with free energy. So Born, even though he felt that he was okay in saying what he said, really did not have a good comeback to his critics. But now, if we can do simulation, let's say we trust Born, incidentally, if I go back to my advisors, I can actually find myself related to Born, because Born is the advisor to Oppenheimer, and one of my great-grandfather was a student of Oppenheimer. So naturally, it was interesting to see if Born is really right or wrong. Well, what you can do is do this simulation, which this was done in around 1997 or so, where we simply just did a constant pressure. Incidentally, these Born criteria are all derived on the basis of 0 loading. And now, of course, people are interested in knowing what is the material strength. So they actually put external loads on systems and watch how they deform. In that case, you have to be very careful. These criteria are not valid because they're only derived for zero load. But for finite load, there are corrections which are actually important. That's another story we would not follow up on. So here, if you do MD simulation, what you find is that this is, some results for gold, some sort of EA embedded atom method potential, standard potential at the time. If you just look at the lattice parameters, so this is the lattice parameter along the X. It's a cubic crystal, FCC, so the three lattice parameters all behave in the same way as a function of temperature until you get to this point. There is a bifurcation. So if you do nothing else, you realize something interesting is happening here. It turns out that two of the three lattice parameters increased, one of them decreased. So you go from cubic to tetragonal symmetry. And the system just did that. Okay? And then the question you can ask, well, Born didn't say anything about symmetry breaking, but he did talk about C44, so let's go and calculate C44. And as I said before, there are two shear moduli. Let's call this one G. Let's call this G prime. The tetragonal versus rhombohedral. So we can calculate all these elastic criteria as a function of temperature. And this is what you find on the lower scale here. Oops, sorry. My thumb got a little nervous. The wrong way. So the bulk modulus didn't do anything. So if you plot the bulk modulus, all the shear modulus, all the G is the C44, G prime is the C11 minus C12, you notice they actually change as a function of lattice parameter. And the lattice parameter itself correlates in a one-to-one fashion with temperature. So this is essentially a plot of the elastic constants of the sample GO as a function of temperature. So you can follow this extrapolation and say, at what lattice parameter does the elastic constant for bulk modulus go to 0? You notice that the first elastic constant that goes to 0 is this G prime, which is C11 minus C12. Let's forgive Born for not worrying about the difference between C11 minus C12 versus C44. They're both sort of shear. Okay, let's not worry about that. So shear, G or G prime, it's okay. But we can tell, indeed, there was a vanishing of this G prime at this lattice parameter, and which coincides pretty closely with what you saw in the breaking of the symmetry. Okay, so this is an indication that Born may be onto something after all. And indeed, if you now look at what the simulation gives you, you find that as a function of time. So this is the I can't hardly read. This is the elastic constant. This is essentially the same plot, but on a different scale. This is a function of temperature. This is now sitting at the bifurcation temperature and watching what happens to the system as a function of time. So this is like watching the onset of this instability. It didn't happen instantaneously. It happens after a while, which is interesting in itself. In other words, the system knows it's supposed to melt, let's say, but it takes a while for the whole thing to start responding. Nonetheless, what you find is that this C11 minus C12 going to 0 is exactly at that point. Okay, so this corresponds to a shear instability. And you can say, well, if you call that a melting transition, then Born was right. However, what about the latent heat and latent volume? Well, that didn't come until later on, because now instead of plotting the elastic constants like up here, you plot the Hij is the tensor that describes the shape of the simulation cell. So when it goes from cubic to tetragonal symmetry, you can also know that there's a shape change, and so the shear modulus kicked in here, and the shape change didn't start kicking into. So there's a little time lag there, which may be interesting for some of you. But now, if you look at the volume of this simulation cell, it goes like this, and then it takes a jump. So indeed, what you find is that there's not just one instability, but there's a sequence instability. They're all connected. One triggers the other. So the thing that you learn, which you couldn't have learned unless you have this kind of data, is that everybody could be right. You could have the shear as the trigger, and then you can have the volume, which is the latent volume everybody expects. And you can have essentially all these instabilities, because you're not supposed to think of these instabilities as a standalone. All right, so right away you have a much more detailed picture of what's going on, which allows you to at least investigate the sort of criticism that Born was subjected to. Now let's go back to the free energy aspect of melting. So if I really want to know the melting temperature, and I can do free energy calculation, which I could do, for example, in the case of silicon, Stillinger and Weber in 1985-ish came out with the Stillinger-Weber potential, which is a three-body axoteller potential, which maintains the silicon in this diamond cubic structure. Okay, with that potential, a year later, Broughton and Lee in 1986 just did a free energy calculation in which they calculated the free energy of this is for silicon, of a crystalline silicon, and the free energy of a liquid silicon. As you would expect, if I plot the free energy as a function of temperature, you will see that at low temperature, the crystal, the solid one, is the lower one, and then the liquid one is the higher free energy one. And if you trace out to height, there is actually a sort of coexistence. They cross so that above certain temperature, the liquid has a lower free energy. That's precisely the meaning of melting in a thermodynamic sense. I remind you, in this calculation, they didn't have to say how does a crystal melt. They simply were interested in predicting the free energy, which didn't care about mechanism. So basically, it's a purely energetic calculation, the free energy. Okay, and this is somewhat
surprising. We think it's a coincidence. The predicted free energy calculation using this Stillinger potential is within 30 degrees of the actual experimental melting point. That was too good to be true, so it's got to be a coincidence. Nonetheless, what it does is that it tells you that you can calculate using this method. You can do a prediction of the melting temperature, or you can now go ahead and do a real simulation, MD simulation, whereby you investigate what is the mechanism. In particular, there was a lot of discussion at the time about the role of surfaces. When you put something into an oven, that something is always finite size, so there is always a surface. And then the question is that how do we know that the melting didn't occur on the surface first, and then the crystal melt interface simply propagates into the bulk? Well, you can investigate that with simulation, because you can simply do periodic boundary conditions in all three directions, in which case you eliminate the surface. Or you can do a free surface boundary condition along one direction, in which case you introduce a free surface. And what you find is that when you eliminate the surface, you can superheat. Easily superheat, 700 degrees. So, on this kind of small scale simulations, surface effects are very important. If you get rid of them, the system will not melt. However, if you now put in a free surface, or you put in some grain boundaries, you put in some defect, it cannot be a small defect like 5-particle void. It has to be a 13-particle void. But if you put in big enough defect, you would nucleate the melting. And then melting would then progress
in a nucleation and growth manner. So what you'll find that in this particular case where you put in a free surface, you will find that there is a crystal melt interface that starts on the surface and starts to propagate at some velocity into the bulk. Now if I take this velocity, and if I measure it accurately, I have these points here. And the interesting thing is that this is a poor man's way of not doing free energy calculation. I simply do an MD simulation. I take the velocity, let's say I have 5 or 6 points. I extrapolate the velocity to a 0 value and get a temperature and call that an extrapolated temperature. And then it turns out to be very close to the melting temperature from the free energy. That's no surprise because when the velocity is 0, that means the system is in a coexistence state between the liquid and the solid. So if you set up an interface, the interface doesn't move. That's when the velocity goes to. So instead of calculating what that point is, you simply just do a few points and extrapolate. Okay, so this basically tells you that if you could somehow examine a phenomenon playing all kinds of what-ifs, and you can investigate all these questions, you might find consistency in some unified way of understanding what's going on. That is my hope of using this as an illustration. Let me see. Maybe there's one more. Yeah. So this is my answer to say, okay, what's the big deal? What have you learned about melting that we didn't already know? Well, here's my my summary about what we learned from that particular study. Actually, it's a couple of studies. We can now say with justification that there are actually two kinds of melting. One is we call the thermodynamic melting. It's actually a heterogeneous process, nucleation growth. That means the surface or any kind of defect will be important. And it's free energy based. Okay? And so, moreover, we also know that if you don't have defect nucleation, then you can actually suppress this melting. That means you bypass the thermodynamic melting, which traditionally is lower than the second kind of melting, which we call mechanical melting, which is really not melting in the true sense of the word. Melting is really upper limit of metastability. So the mechanical melting, the second, is actually a oops, I'm going to do that again. It's actually a homogeneous process, and you can verify that just looking at the simulation. When melting occurs under mechanical melting conditions, the defects just come and go. They just pop up everywhere. So it's clear that it's a homogeneous thing. Whereas it's also clear that in the heterogeneous case, if you put in a surface, the melting commences only on the surface and then it propagates in an orderly fashion. So knowing whether a process is homogeneous or heterogeneous can tell you a lot about what's going on. And then finally, you can say that this is a bit of a unification or demonstration of Born's two criteria, 1939, 1940. But this 1939 criterion based on C44 or C11 minus C12 should only be applied to mechanical melting. So in that case, Born and his critics are both right. They're talking about different problems. Okay, so I now move to the second illustration, which is one that I will probably take a little longer. Let me check with my host, Nicola, to see how
15, 20.
Left?
Yeah.
Okay, that means I used up more than I should have. My tank is going empty fast. Okay, 15, 20 minutes is fine. What this means is that I have a few slides with some details, which I think, I hope I can just hop over, because the main message is really what I would like to sort of get over, and I think I can do that with the time remaining. All right, so I said it's a 40-year-old question, and indeed, Martin Goldstein published this very nice paper in Journal of Chemical Physics, 1969. Okay, so my math is bad. I guess it's a 45-year-old question or something. Right? Sorry. Yeah. So, but the title is interesting. The viscous liquids and the glass transition. That part is okay, but the really telling is the potential energy barrier picture. We hear a lot about potential energy landscape, potential energy surface, being a multidimensional hypersurface in the variables in the variables of the coordinates, atomic coordinates of your system. So it's like a 3n dimensional space. And a lot of what we know, if you take a materials scientist perspective, is all coming from microstructural evolution. And microstructural evolution basically refers you back to the potential energy landscape in terms of where the minima, local minima, where the saddle points and activation, what have you. So, quoting Goldstein, who at the time was complaining about, there was this argument between people who were involved in thinking about the glass transition. The argument was between the free volume theory and the so-called entropy, the free volume model and the entropy model. Both camps have their own arguments, and people were just, going back and forth. What Goldstein suggested was that that's not the problem. He said, let's now think more broadly than just these two particular versions of how you would explain things. They could be both right, they could be both similarly wrong. He said, let's now focus on the potential energy landscape. And as part of what he was interested in, he said, in my opinion, I believe viscous flow is dominated by potential barriers high compared to thermal energies. So in addition to saying that let's focus on potential energy landscape, he was also saying that let's focus in particular on activation, on finding out the peaks on the landscape terrain, because those are the saddle points that you have to go over. And as soon as you say that, you realize there's no longer a thermodynamic issue where you worry about the minima, the valleys. So here is a problem where kinetics will matter, the kinetics of activation. And keep that in mind, because as we're going to go further, we will find that indeed is the sort of the picture of what's so mysterious about glasses in terms of their shear viscosity. Okay, so the picture is coming. There are two others who also made very profound statements about the glass transition and viscous flows. And so the next person is Austin Angel, who wrote a paper. So Goldstein's paper was 1969, Austin's 1988, some 20 years, 19 years later. He simply called his this particular article the perspective on the glass transition, and the reference is given here. This is a classic paper. Everybody knows that because everybody knows the so-called the Angel plot of shear viscosity, and this is the Angel plot. You see a mass of data in which Angel called attention to two particular behavior. There is something that goes in Arrhenius. So this is a plot of log of the viscosity versus 1 over the temperature. All right, and so there are two or three data you have to look carefully. But silica, for one, vitreous silica, SiO2, follows these symbols here, and I think some of these other oxides as well follow them up here. So you see a sort of a straight line Arrhenius behavior because I'm plotting log here, right? So the temperature behavior, the viscosity as a function of temperature. By the way, this is the temperature to which you quench, you supercool the liquid, not the temperature from which you started your supercooling. So this is the quench temperature. What this data is telling you is that as you lower the temperature, which means you're moving from the left to the right, the viscosity goes through the roof. 10 orders of magnitude, 15 orders of magnitude. And that's a lot of change. So the question in those days is that what's going on? This has to be some kind of cooperative phenomenon. But what is it?
So people tend to think that if you can explain the so-called fragile behavior, why the viscosity can shoot up, let's look at the so-called fragile liquid according to Angel. So the viscosity has this kind of Arrhenius-like behavior. This is, you might call it strong. And at some point, you have an upturn, you have a turnover, and it goes up like this. And this is called fragility, okay? And whereas this is called strong. So Angel basically told us, experimentally speaking, there are two kinds of behavior you guys better be able to explain. The strong behavior and the fragile behavior, because they're not the same. Okay? So the issue becomes a little more complicated. Namely, we're not talking about supercooled liquids, glass-forming liquids, but these supercooled glass-forming liquids can be sort of classified according to two classes, the strong behavior and the fragile. And any theory, any kind of concept should be able to explain both on equal footing. You cannot just say, let's worry about fragile, forget about strong. No. If you have a full explanation, that better be consistently dealing with both. Okay, so now the third person, actually De Benedetti and Stillinger are the author of this paper in Nature 2001, so this another some years later than Angel. This is a review paper which is just simply called Supercooled Liquids and the Glass Transition. And they pointed out that one intriguing aspect of the so-called glass transitions, when you think about it, it's really there's an interplay between thermodynamics and dynamics. You can replace the word dynamics with kinetics if you like, because that's what we saw. Mechanical melting versus thermodynamic melting. One is thermodynamics, free energy based. The other is kinetically based, because it has to do with the mechanism of vanishing of shear instability. So that kind of theme, that kind of thinking carries over in the glass problem as well. And De Benedetti and Stillinger went right to the source of the problem, the challenge, namely, explain this. This is now, this is germanium dioxide, silicon dioxide. These are the data. Clean out all the other stuff and a whole bunch of 7 or so liquids. They're color-coded. That's this fragile behavior. So they say, well, the strong behavior is an Arrhenius behavior. The fragile behavior is this sort of curved line plotted in this way. Now go and explain this. So I'm going to take that seriously, and I'm going to just call that the Goldstein-Angel-Stillinger challenge for now. Okay? So the challenge I'm just going to state again in a simple sentence. Can anyone perform a molecular calculation, which means no cheating, no fitting, which means you got to start out with some kind of potential. You got to do molecular calculation, sample the energy, potential energy landscape, do whatever you have to do, but nothing ad hoc. You cannot assume a vocal Fulcher expression, because that's sort of not allowed here, right? So you got to do a full-blown, real, bona fide molecular calculation. The calculation based on potential energy landscape, that's not such a stringent requirement, but the calculation must explain both the fragile and the strong. So that means that you have to at least explain the kind of behavior that we set out with this, and this. So this is why we call it the Goldstein-Angel-Stillinger challenge. And now I'm going to check my time with my host to see.
10 minutes.
10 minutes, okay. So no, the race is on. So this is obvious. Let me tell you the upcoming story. A few slides left. I'm going to tell you about two calculations. One is what we call heuristic calculation. It means it's physically transparent. It's very conducive to learning, and it's kind of insightful. That's the one based on transition state theory.
in which we calculate the viscosity in terms of calculating a temperature-dependent effective activation barrier, treated like an activation process. We already knew that, that people have been thinking about that. Now that calculation has been done for both the fragile and the strong liquids. Two separate calculations. You can compare them afterwards. Okay? So in that sense, it's a systematic calculation of these two behavior. Since it's using the same approach, we call that an explanation based on this heuristic approach of the second calculation is for the purist who said, no, we don't necessarily buy transition state theory, but we like linear response theory, Green-Kubo expressions. That's well known in linear response theory, that you can calculate transport coefficients by doing the Green-Kubo formula, which is essentially calculate the stress-stress correlation function, do its time integral, get the shear viscosity. And that's the second calculation that we've also done. But you know what? The second calculation is sort of theoretically, or I would say formalism-wise, is more justified, more rigorous. It actually includes some of the entropy effects. The first one sort of ignored, and actually gives better agreement with the experiment. But it doesn't quite have the physical transparency of the first one. So I like the first one. I'm going to describe the first one by waving my hands. I'm going to flash the second one and just say, okay, believe me, these things are now published, and feel free to go read about it. We can talk about it. Okay? So I assume I'm still have about 8 minutes or so. I'm going to sort of wind my way through. So here comes the answer to this question. All right? So this is I'm not going to say much unless somebody wants to stop me or talk about it afterwards. So basically you use transition state theory, which says you can write the viscosity as a function of temperature as some prefactor times an exponent of an effective activation barrier which is temperature dependent. You notice if Q of T is temperature independent, you just get Arrhenius behavior, and that's the strong behavior. Okay, so if you can explain the strong and the fragile behavior, then your first question is, what does Q of T look like? Is it any simpler than the viscosity? And you should expect that the viscosity goes over 10, 15 orders of magnitude. Q of T doesn't have to do much because you're in the exponent. So that takes a lot of the variation out already. Okay. So having said that, then let me now sort of bypass how we actually do this. There is a method due originally to Liao and Paranello called metadynamics, which is a way of sampling free energy landscape. In their case, they use it on the molecular calculation where you know what the natural coordinates is, not the whole coordinates of the entire assembly of particles, but the coordinates that are relevant to a particular molecule, like a conformation of a molecule. But this method can be adapted to look at this problem, and that had been done. But basically, the method is just illustrated here, and this figure is well known from Liao and Paranello. It basically asks you to start out with a system in a particular minimum, and it has a bunch of saddle points nearby and nearby local minimum. You can reach these nearby local minima by activating through some kind of energy penalty function, and then through a series of activation and relaxation, you can force the system to go up this barrier and then climb over the saddle point and fall into the next minimum. And you have to check to make sure that is a true saddle point and not a saddle point due to the potential energy with the penalty. So you're supposed to take off the penalty, otherwise it's biased. Okay, so there are some fine points here. But if you use this, you generate, this is one way to talk about the free energy, not the free energy, potential energy landscape. You see a sequence, this one particular sampling of a potential energy trajectory on the landscape, where you see a series of minima and saddles and so on. And so you can see that there's some low minima, like a basin from here. There's some high saddle point over here. But let me skip over the details and just say that if you use this method, which is no longer molecular dynamics, it's metadynamics, you can generate data of this kind. And then with this data of this kind, you can do activation barrier analysis in which you actually take seriously the statistics of the various activation paths. So if I start out with minimum I, and I want to know what is the activation going from I to J, and I notice this is the highest saddle on the path, and that defines the Qij. There are all kinds of combinations of Qij for various J's and so on. So this becomes a sort of a statistical analysis. But at the end of the day, you can come up with the activation energy as a function of the initial state where you start. But then this only gives you the activation part. But remembering now that the glass transition is not only just the dynamics, it's also thermodynamics. In the early days, Stillinger-Weber had talked about the so-called inherent structure. And that's supposed to be applied to liquids, about the underlying energy level of the liquid. So if you take now that seriously and take it to the supercool liquid, you can now incorporate this thermodynamic information and come up essentially with this activation barrier. So this activation barrier Q of T, which is the quantity here, very simple. At high temperature, it's very low activation. It's almost like a two-state system. All right. At high temperature, you have very low activation, and then the activation climbs very steeply up to a high energy level at low temperature. And part of that steepness comes from this inherent structure, which is the one that tells you about the correlation between the temperature of quench versus the energy minimum. That's the inherent structure. So both the activation, which has this kind of behavior, and the thermodynamic contribution play a role in giving rise to this. Is this any good? Well, if you put this into this expression, you get this line, this dotted red line here. I guess it's not dotted. It's dotted. So you get this line here, and here's the data. So you sort of capture the fragile behavior. Not very well, but keep in mind that this simulation was done with the binary Leonard-Jones potential, the so-called Kolb-Anderson potential. It was not fitted to any of these fragile liquids. In fact, so it was not intended to give a very good description. Nonetheless, it seemed to capture the qualitative behavior. Okay, so now we have applied the same thing for silica. So now I'm going to go to show. In the case of silica, here are the results. The line is the effective potential result for silica, and these blue points are the ones from Angel plot or from the Di Benedetti-Stillinger plot. So you can see they give a very good description. There's a little kink here, which is a kind of a point for the specialist. We actually believe that the experiments, which could not be done to a high enough temperature to go below this, if they could, because apparently at this temperature, this thing catches fire or something experimentally. So you cannot really extend that. But if you could, we actually predict there is a crossover from strong to fragile here, and then back from fragile to strong. And there's evidence of that from some MD simulations at this low viscosity. That's just a note. But the point is that through this particular expression, we can explain pretty well the qualitative behavior, or even semi-qualitative behavior of the shear viscosity. So now let me step you through the. So this is one of the outcomes which I would just touch on now. If you can do a calculation on two systems, which is actually based on potential energy sampling, what have you, you can begin to look at the topography of the potential energy landscape. Things like, disconnectivity graphs, which look like these trees, and which is over here. This is for the fragile, this is for the strong. They look quite different. Or you can just analyze these trees and do a cut across. You get this kind of potential energy profile. You can see this is now, we're giving a quantitative meaning to the ideas of potential energy profile for fragile and strong liquid, which was first put out by Schillinger back in the 80s, 90, and in which he just sketched. This, he said, was a very smooth landscape. He called that for the strong, and this he calls a rough energy landscape. He calls that for the fragile, and this is based on the quantitative calculations. This is what we get for the rough, comparing to here, and this is what we get from the strong. So there is some kind of a qualitative correspondence. That means Schillinger was not off in the sense that he missed anything, but he just didn't really quite have the quantitative information at the time to substantiate his beliefs. Now, I'm going to skip over some mechanism parts, which just to show you that you can now begin to look at how the atoms move when they start to activate, like string motions, line motions, which have come on discussions of melting. And also, when you do it for silica, which looks very much like silicon, you also see interesting bond exchanges and bond rebonding. So these are things people had known about network glasses versus molecular glasses, and these things are also coming out of this simulation. So I will now, I think I'm on borrowed time already, so I'm going to end 5 minutes. So this is the Green-Kubo network calculation. Basically, by network, we simply means you can imagine there's a network of nodes, various sites, and the sites go from one site to another site through some kind of activation. So if I have activation energy from the lower part, I can map this information onto a matrix whose elements are the activation probabilities. Okay, so once I know, so I can now formulate this in some kind of a coarse graining fashion. I can do that in the master equation. And actually, we can solve this equation sort of analytically and reduce this calculation to a numerical calculation. Numerical calculation gives us results like this. So this is the numerical calculation. By the way, to get this curve, you actually have to break the temperature range over 4 different parts, because there's a lot of change in the details that you cannot possibly hope to capture everything with one sampling. So you basically take the energy range of interest, you sample in 4 different regions, and then you calculate using the same approach with different inputs, and then you connect them. But nonetheless, you get something that's pretty good. And now if you take the data, some people have taken 15 liquids and fragile liquids, and these points, these symbols, are experimental data, and this red curve, admittedly, is not a raw data plot, but it's a plot based on some kind of reduced data. There, you can see this red curve goes through this fragile behavior pretty well, and you can also identify some kind of a crossover temperature, which Austin Angel was trying to suggest. Instead of the glass transition temperature, which is a sort of arbitrarily defined temperature, that's when the supercooled liquid has a viscosity of 10 to the 13 poise, but there is really nothing physically significant. What's more interesting, as suggested by Malamache and Stanley and others, is this crossover temperature. And mole coupling, this is to remind me to mention that those of you who follow self-consistent mole coupling theory, a la Goetze, mole coupling theory would actually predict a sort of transition temperature somewhere here, which is right near this knee here. And physically, you can actually imagine what's going on here is a manifestation of stress localization. Now that's maybe a little far-fetched, because what does localization mean? Here, what we have in mind is that when you quench the liquid into a low temperature, the liquid falls into a deep minimum. Okay, and that deep minimum means that you have to wait a long time before you can climb out of it. That long time wait means that the local shear stress is localized. When the shear stress is localized, that implies physically the stress-stress autocorrelation function doesn't decay very fast. And that's the reason why the viscosity is going through the roof. The correlation function has a very slow decay. And when that happens in diffusivity, you call that structural arrest. And the diffusion coefficient goes to 0. Viscosity becomes very, very large. So there are natural connections here. I know I'm on borrowed time. This is my last, I'm not going to do that one. So this is my last slide. So I've told you a lot. I think I have, but I'm not sure it's clear. But let me just try to go back to the initial curve about the mesoscale. So I've told you about melting. I've told you about glass transitions, supercooling. There are other phenomena you can talk about, and I give you, three examples here. One is creep phenomenon, the other is corrosion, and then cement setting. So these are all very different phenomena, but they share some common issues, some common challenges. And the basic challenge is that they all have to do with slow dynamics. And what is that? Slow dynamics. Well, about in the late 70s, there was a burst of interest on a concept which has to do with how sand piles behave and how do you model sand pile, and it has certain scaling relation. The concept has come to be known as self-organized criticality. Self-organized criticality was very popular for about 20 years until people realized that it wasn't going to tell us everything. All right? So there are now people who believe self-organized criticality, there are people who don't. There's a lot of debate. But what is interesting about self-organized criticality is that you can now replace that concept by this thing here. And what is that thing? So this SDIDTS is a term coined by Jensen, who wrote a book on self-organized criticality some years after Pierre Bach wrote his book. That stands for slowly driven, interaction-dominated threshold system. Okay? Now, that is very, very different from self-organized criticality. Self-organized criticality basically says you have self-organization, but you have criticality. This is a different view. This says that you should pay attention to natural phenomena which are driven. So it's not just self anymore. There is some external perturbation. Everything is being driven, whether it's temperature, stress, chemistry, what have you. Usually the drive is slow. And then, but it also is dominated by interactions, internal interactions. So you have a balance. You have the internal and the external. And the most important thing is the threshold system. So we're talking about systems which are always on the threshold. And that's what we mean when you have something that goes, like the viscosity goes from this behavior, all of a sudden shoots up. That suggests very, very simply that there's a change here in the mechanism. For example, if I were a transport person, I would say, well, the change in mechanism is going from continuous collision, as we know from hydrodynamics, as you would have in a liquid, to hopping over barriers, or in the case of stress localization. Same thing with creep. With creep, what you plot here is strain rate as a function of the driving stress. Again, you see this distinction between this kind of exponent and this kind of exponent. So here, the exponent is 1, and here is exponent 10. So you go from a very slowly varying creep rate with stress, which is not that worrisome, until here, when you get into a creep rate that's varying with a power of 10 to the stress, that's very, very worrisome. With stress corrosion cracking, it's the same sort of behavior here. I won't get into that. Also, same with cement setting. So basically, what we're saying is that we're now dealing with a range of phenomena, all of which may be, wrapped into this thing called the mesoscale science frontier. And the buzzwords that you can use now, and I think they're no longer buzzwords, they actually have some real meaning and real challenges, would be things like localization or jamming. Jamming is a term people talk about a lot with granular material. Localization, you can do many phenomena with that. Intermittency. Now we haven't, one of the things that I was going to stress, if there's time, from the standpoint of simulation, our big challenge, and this I'm trying to say it to Dominic, is we do okay on the spatial part, but we do not so well on the time scale part. We need to get away from the short time steps of MD simulations. And that's where slow dynamics takes us. Okay, so with intermittency, that has to do with the rate effects, also intermittency, rare events, avalanches, and so on. And finally, people who do neutron scattering know a lot about dynamical heterogeneities, going to higher order correlation functions to look at some of the things that people now can measure. So with that, I guess I really overstayed my welcome. Nicola may not want to speak to me anymore. But I really had a great time, and I want to thank you very much for coming.
Now, thank you, Sid, for coming over an entire ocean. We have time for a couple of questions to get the discussion.